Hello and welcome to lesson 4 from topic D1, simple harmonic motion. In this lesson, we're going to be talking about mechanical resonance. We're going to be introducing it, and then there will be a follow-up video where we look at an example involving mechanical resonance. So, as we already know, when you start something like a pendulum swinging, it will move back and forth at a set frequency. And we can calculate what this frequency is using the formula T is equal to 2 pi multiplied by the square root of L over G. If we want to figure out the frequency instead of the period, well, frequency is just going to be equal to 1 over the period. So if you want to figure out what frequency something is going to vibrate at, well, that's relatively straightforward to do. The same thing happens when you bounce a mass at the end of a spring, or even if you're walking while swinging your arms. Your arms tend to act like pendulums, and they will naturally be swinging at a certain frequency. This is where the term natural frequency comes from, because it's sort of the natural way that things move. And we can abbreviate this as Fn, where of course n is the natural frequency. But of course, it's not always the case that you would just start something moving, walk away, and never touch it again. So quite often what happens is that you are going to be applying an external force to the oscillating object. For example, pushing somebody on a swing. When you're doing this, you are applying a force to the person. And specifically, in this case, we're going to be talking about cases where we're applying a force in sort of a repetitive manner. So for example, when you're pushing someone on the swing, you push, you let go, they come back to you, you push again, and you repeat that motion. Another example of this kind of force that is going to be applied to an oscillating object would be something like an earthquake. As the ground moves back and forth, it's going to cause the buildings that are built on that ground to also oscillate back and forth. And so in that case, the earthquake is going to be applying an external force to the oscillating object. So this external force is going to affect the amplitude of the vibration. So for example, if you're pushing somebody on a swing, going to affect how high they go, depending on how you are pushing them. This external force, we use the little symbol FF to talk about the forced or the forcing frequency. So this is how often you are pushing on something. And then, of course, as soon as this applied force stops, we return to the natural frequency. So if you stop pushing someone on the swing, they're just going to continue to swing at that natural frequency again. So a couple of pieces of vocabulary to keep in mind here is natural frequency and forced frequency. When we're talking about mechanical resonance, what this is when the forced frequency is the same as the natural frequency. So let me just write that down. When F, the forced frequency, is exactly the same as the natural frequency, then we observe what we call mechanical resonance, or sometimes we just call it resonance. And what's happening with mechanical resonance is that the amplitude of the oscillation will increase but the frequency stays the same. And just to think about this, so again, we can think about pushing somebody on a swing. This is kind of the easiest example to understand this. And I'll just write this down, pushing someone on a swing. In this case, the frequency that you want to push them at, if you want them to get really high and to have a fun time swinging on the swing, you want to push at the same frequency as the swing is oscillating. In order for their amplitude to increase. If, for example, you tried doing something different where, so let's say you push them at the wrong time, well, what's going to happen? Well, their amplitude is obviously not going to increase. So if you push them just as they were coming back to you instead of as they were starting to move away from you, you would sort of counteract the natural motion of the swing and you would decrease the amplitude instead. So you have to apply the force at the same frequency as the natural frequency in order for this resonance to occur where the amplitude is increasing. This is the same sort of phenomenon that occurs with something like somebody trying to break a wine glass with their voice. And we've got a video linked below as well that we can take a look at. But for example, let's draw a little picture. Oh, this is a terrible picture. We've got a person, and they are emitting some waves. And we've got a wine glass that they are trying to break with their voice. So this wine glass, I better add labels so people know what these are. Wine glasses, we'll just say wine glass. And human voice. The wine glass has a natural frequency that it vibrates at. So for example, if you hit the wine glass with a fork, it's going to vibrate at a certain frequency. If someone is able to replicate that frequency with their voice, well, then they will be able to cause resonance within the wine glass, causing the oscillations of it to increase more and more, in which case it could break. So this is kind of why you are able to break wine glasses with your voice, is because you apply a frequency at the, a force. In this case, the force is coming in the form of sound waves, and you apply it at the same frequency as the natural frequency of the wine glass. This also is a concern with something like an earthquake. If it is causing a building to move at the same frequency as the building's natural frequency, then this is where we can end up with some disastrous results. And there's all sorts of ways that engineers take advantage of these. So that's all there is to know about resonance, is that the amplitude will increase if the two frequencies are the same. If the forced frequency is different from the natural frequency, then that amplitude is not going to increase. And we've got a couple videos coming up with some examples of this, as well as a example where we actually calculate the natural frequency of an object. So we'll leave it at that for now.